So welcome to video 1 for gas laws. I'm going to go through these a little quickly. This is a review from last year for advanced chemistry, but we're just going to cover the basics today in this first video. All right, let's go ahead and get started. Okay, so first thing we're going to talk about is gases in general. So we live in a solution of gases in the atmosphere: nitrogen, oxygen, other gases. In this chapter, we're going to focus on the behavior of these gases and kind of the laws that go along with them. We'll talk about the basic ones today, and then we'll get to ideal gas law in the next video. So first, pressure. So gases are compressible. Liquids and solids are not. Gases uniformly will fill any of their containers, similar to the way that liquids do, but they'll fill the entire container. Gases will mix with other gases, but their behavior with each we're going to treat as though they are actually ideal, which is inaccurate, but it works for our purposes. So a couple of instruments that are used to measure gases. One of them is the barometer. So in 1643, Torricelli invented what we call the barometer. It's an instrument for measuring what the atmospheric pressure is. So over here on the right, this is what a barometer, a basic barometer, looks like. You wouldn't see one of these, but this is kind of how it's set up. Over here on the right, so what we have, let me get this pen turned on here, is the atmospheric pressure is actually pushing down this way on a pool of mercury. Now, any liquid could have been used, doesn't really matter, but mercury, doesn't evaporate at room temperature. It won't go down over time. The volume won't go down over time, so it's best. But it pushes down on the mercury and forces the mercury up the tube this way, and then there would be graduations on the actual tube so that you can measure what that difference in pressure is. And so as the atmospheric pressure increases or decreases, the volume of the liquid in the tube will go up or down. And so down on the bottom is that dish filled with mercury, and then there's a closed tube. The outside pressure causes it to go up and down, and of course you can measure the atmospheric pressure. Another instrument, which we're not going to use, is called a manometer. Manometer is very similar, but it's actually used for measuring the gas pressure of volatile liquids. So this is kind of what it looks like down here on the bottom right. So this is a manometer down here. The gas is pressed in here, or the liquid is pushed in here, and it gives off as a gas. As that gas pressure goes up here, it forces against the atmospheric pressure. This part up here at the top is actually open to the atmosphere, allowing atmospheric pressure to push down here. If that value is less than the atmospheric pressure, then the height will be lower. If the atmospheric pressure is less than the gas pressure or the vapor pressure of the gas, it will actually increase. And so gas pressure is either going to be a subtraction of that height difference, that column difference, or an addition of that height or column difference. Again, you'd have graduations on here to measure what that value is. I don't have a manometer to show you guys, but just to tell you, this is another device you can use to measure. Actually, other gases, if you already knew the atmospheric pressure, you can measure their vapor pressure. So the units of pressure, you guys have to memorize these. I said that out loud, didn't I? You actually don't have to memorize these. These right here are actually given to you on your formula chart. The 760 millimeters of mercury is the same thing as 760 torr, which is equivalent to 1 atmosphere of pressure. Those you have to be able to convert from unit to unit. The other unit you will have to memorize if we're going to use it. It's not going to be given to you, but it's the number of kilopascals that's 1 atmosphere, or 760 millimeters, and that's 101.325. We'll just use 101.3, same as we have in the past, but you'll see kilopascals or pascals mostly in physics. You won't see it so much in chemistry. In chemistry, we typically use millimeters of mercury, torr, or atmospheres, but you may see it in kilopascals in some of your other classes. You do need to be able to convert between any of those 4 units, but that's pretty simple stuff. So the first of the gas laws is Boyle's law. This comes in the 1600s. but pressure and volume are actually inversely related. As one goes up, the other is going to go down. So if you increase the volume, you decrease the pressure on the gas. If you decrease the volume, you make it smaller, you would increase the pressure on the gas. You can, excuse me, you can use either of the two formulas that are listed down here, but the one I'm circling is actually the one we most often use. Believe it or not, this formula is not given to you on your formula chart, which I find kind of strange. The chart has changed over the last several years, but even the combined gas law is not given to you. So when we get to it, I'll remind you, memorize the combined gas law and then just cancel out the things that are constant. But in this case, temperature would be constant. So when temperature is held constant, the pressure and volume are inversely related. So just a little bit about the way we're doing this. There are laws that kind of govern gases and take into account the behavior of the gases. What we're going to do through all of the calculations that we do in AP Chem is treat the gases as though they're ideal. Now, this graph is a little misleading. If you look at the y-axis over here on the y-axis, there's really not very much change from 22.25 to 22.45. So when you look at these three gases, they're all nonpolar substances, right? Neon, oxygen, and carbon dioxide. Carbon dioxide would have the greatest number of polarizable electrons and therefore the greatest LDFs. That's why it deviates from the ideal behavior. What we do when we say things are ideal is that they don't interact with each other in any way. And so while it makes it easy to treat gases this way, and most nonpolar gases do behave this way, there is slight deviation from what we consider to be ideal. However, when we do all of our calculations and stuff, we're just going to treat them as though they're ideal, and that it would be constant. If you look there at 22.42, which is right here, that is actually molar volume of a gas. So we say at standard temperature and pressure, which is 0 degrees Celsius, and 1 atmosphere, which is over here on the far right, we say it's all 22.4 or 22.42, but that's not actually true. We're excluding intermolecular forces and the sizes of the molecules, but it's okay. For what we're doing, it's fine. So yeah, the CO2 does actually show the largest change, but the pressure and volume changes is really quite negligible. It's pretty much the same. The volume's not really changing that much for that change in pressure. So we'll use 22.42. You'll see interchangeably 22.42 and 22.4. Your AP formula chart does list a molar volume of a gas as 22.4. It doesn't actually use the extra significant figure, but that's okay. That's all right. So that is your molar volume of an ideal gas. So at standard temperature and pressure, and I do believe this is also, let me double check while I'm sitting here with the formula chart in front of me. Let me double check that they actually say what the values of STP are. They give it to you as 273 K and 1 atmosphere. They do actually give you these values on your formula chart. This is tragic, in case you've forgotten them. Yeah, okay. So Charles' law is the second one. So we have Boyle's law, pressure, volume. When the pressure stays the same, the volume and temperature are directly proportional. And so, but you cannot manipulate the pressure. It has to be at a constant pressure. Usually the constant pressure that's used for these experiments is just going to be atmospheric pressure. So if you just do these in the room or, do your experiments at the same time with the same atmospheric pressure, it stays constant. And so the only things that would be manipulated would be volume and temperature. Do not forget the temperature has to be in Kelvin. The reason this is because in an absolute scale, it goes from 0 and only has positive values. Therefore, you can't end up getting negative volume values. That doesn't make any sense not to have any volume, or not to have any mass. Substances, of course, will have volume. So make sure your temperature is in Kelvin. For this unit entirely, we won't use anything in Celsius. You'll have to add 273 and change it. And that conversion also is given to you on your formula chart. So Avogadro's law is basically what we've been saying here. Equal volumes of gases at the same temperature and pressure have the same number of particles. If that temperature and pressure is actually 0 degrees Celsius or 273 K and 1 atmosphere of pressure, it's going to occupy 22.4 liters of gas. For a gas at constant temperature and pressure, that volume is in fact directly proportional to the moles of gas. The only thing that's not proportional, we'll discuss when we get to the ideal gas law. So Gay-Lussac's law is not actually in your notes, but it is relevant. You don't really need to know the individuals' names as we did in advanced chem last year, but just telling you. Gay-Lussac's law is where volume is held constant. When volume is held constant, for example, in a rigid container, the pressure and the temperature are going to be directly proportional. Once again, the Kelvin temperature has to be in kelvins. That way you only have positive temperatures. We can't have things with negative pressures or creating vacuums. That's not a thing. So yeah, just make sure that your temperature's in Kelvin. These calculations are actually quite simple, provided that you have the same units for both sides of the equation. It's fine. You may have to do a little bit of conversion for your Pufnert equations, but we'll talk about that later. And then the last thing in this short video is talking about the combined gas law. You need to remember this one. Pretty easy. We did this last year as well. Pressure, volume, and temperature. Pressure and volume are the only ones that are inversely related, so they're right next to each other. Pressure and temperature, as well as volume and temperature, are each going to be directly proportional to one another, so they're above and below each other. So peas and vegetables on the table is how we remember this. So pressure times volume divided by whatever your temperature value is in Kelvin will equal what's going to happen to it. If you manipulate one of those, values, you'll end up getting a separate value on the other side. Now, if something is held constant, like say temperature was held constant, you would lose the temperature here, yeah, and you would end up with just your Boyle's law, pressure, volume, pressure, volume. You're more than welcome to just input the same values. For instance, if they gave you the volume of a container was 1 liter and it was 1 liter on both sides, you could put the 1 liter on both sides, it'd be fine. But if it's not changing, you really don't need to put that on there. And that's it. So that's that first little video over the basics. That was kind of everything we did last year for sure. But we'll do some more calculations on ideal gas law in the next video.